Good morning to everybody. In this webinar, we will show you various typology of bridge design in accordance with Eurocode. Just a quick presentation of myself and my company. My name is Marcello Colasanti. I am a civil engineer, graduated at the University La Sapienza, Rome in 1996. More than 25 years of experience in bridge engineering. I've been a partner and technical director of one of the most important engineering company in Italy for bridge design. And in 2019, I've founded my company Colasanti Limited. Here you can see some of the projects I've worked on during my career. And in the big picture, the bridge across Buna River at the border between Albania and Montenegro. Let's see now the content of this webinar. This is divided into two parts. In the first part, we will see a Midas civil overview, pre- and post-processing, analysis, loads, design, and checking. In the second part, we can see various examples of bridges that we have performed with Midas Civil. PSC rail bridge, masonry bridge, steel concrete composite bridge, tied arch, and one cable stayed bridge. On these two last kind of bridges, we will go deeper in the model. Let's see now the first part, in which we can see the Midas Civil overview for the different possibility that you have to model bridges. You can model using 1D, 2D, and 3D elements. You can use BIM translator. You can import, export in the principal softwares. You can use Wizard for quick modeling for composite bridge, PSC, RC slab, RC frame, grillage, and even cable stayed bridge, suspended bridge. There are wizards for transfer models starting to the global model and rail track analysis. There are elements for strands, wires, roads. There is a library of building device. You can change the boundary conditions during the construction stage. You can model foundations and the soil structure interaction, and you can use table of results for diagrams, export in Excel, in TXT, and so on. Now, just to have a look into the program, we can see here how to define a node and the element that are the basic point for the finite element model. This is the node area in which you can create, translate, divide, and you can do all the operation that you want to do. You can define by coordinates. You can copy a certain number of times. You can define distances between nodes, and also you can define nodes in a table. Regarding the elements, you can use general beam, tapered beam, truss, tension only, hook cable, compression only, gap element, or plate, plane stress, plane strain, asymmetric elements, solid elements, and you define it here, and you can modify with curve elements, translate them, extruding, dividing, merging, intersecting, and so on. You can also auto mesh one single element, and you can change these parameters in the future. You can also see the element table in which all the characteristics of the element can be shown and modified. Of course, also material can be defined. There are some materials in the library, very common, for example, SRC for the steel and concrete structures, or steel or concrete. In the RRC, you can define a different standard and a different database for the single material. So in this example, we can see Eurocode 5 for steel, Eurocode 4 for concrete, C3037, and you have here the values correlating with this standard. So the modulus of Young, ratio, Poisson ratio, thermal coefficient, weight density, mass density if you want to use, both for steel and concrete. If you choose to use steel, you have the same characteristics for the steel, and you can use also plastic characteristic. For the concrete, you can use the same thing. So you can define kind of concrete. All the characteristics have been considered according to the norms. And you have to define also the behavior for the time-dependent effect, obtaining curves for creep, shrinkage, and defining the code that you want to use. You have different codes, European model code and some else. You have to put just the characteristics of the concrete, the notional size, the relative humidity, the type of cement, and the type of code that you want to use. And this is one of the main points of the bridges, in which generally composite beams are realized in different stages. Composite beam could be realized with part 1 made by concrete or made by steel, and the part 2, that is the concrete slab. Concrete slab is poured over the part 1, and we have different characteristics of the cross-section in different stages. So this can be done specifying the construction stage at which the composite section defined become activated, and we can define the part 1 when will be active and at which stage will be active at part 2. We can also define the age of the material when it will be active, if it is 3 days or 28 days for the concrete, and we can analyze this situation, correlating that with the general construction stage that we are going to define. For the analysis, you can provide the static and dynamic analysis and nonlinear analysis, time-dependent material, so creeps, shrinkage, relaxation, and the plastic material, masonry material. You can provide analysis for P delta, buckling, eigenvalue, geometric nonlinearity of materials, pushover analysis, localized hinges, fiber models, very important construction stages, boundary change analysis, heat of irritation, internal and external stress post-tensioning, backwards analysis for cable stayed bridge and suspended bridge, rail track analysis. The loads are defined in the software. For static loads, you can have self-weight, element and nodal loads, pressure and plane loads for the shell and solid element. For dynamic loads, you can define a spectrum, time history functions, or multiple support excitations. For temperature, pre-stress, you can define uniform and gradient temperature and pre-stress on beams. For the moving load, there are the various models for the different normals for rail, road, and pedestrian bridges. And static loads can be defined in the static load cases through this window, in which you define with the name your static load, and you can add the type of load that you are considering. For example, for wet concrete, formwork, barrier, curbs that are all construction stage load. You have to consider this type in this column, and for temperature you have this kind of type. This is important for the auto generation of the load combination by the software. There's the option also to put a brief description of the loads. And talking about loads, we have to analyze, of course, mobile loads that are the most important loads on the bridges, so mainly typical loads for the bridges. You can define mobile loads according to different norms. Here you can see the mobile loads according to Eurocode. So the model are LM71, SW0, SW2 for rail bridge loads, LM1, 2, 3, 4 for road bridge loads. There are the standard model vehicle for the pedestrian bridge. And it is very easy to define the mobile load on the bridge. You have just to define the lanes connected to the deck and to apply the model load to this lane. Software itself find the most several configuration of the loads, both longitudinally and transversally, in order to find the stress in the element that you are going to assess. And this is an example for the Eurocode. This is a load model 1, the characteristic value of the load model 1 for the road bridges. And here the window for the definition of this model, in which you can find the same value that you can find here in the table, and also you can apply the factor psi to evaluate the frequent value of this load. And once you have defined the lane, for example in this case 3 lane and 2 footway lanes and 1 remaining area according to the Eurocode, you can define the moving load case, applying the characteristic value of a typical load model, in this case load model 1, ignoring psi factor if you are considering the characteristic value, or not ignoring if you want to consider the frequent value, and apply to the selected lanes and applying the remaining area in the selected remaining lane and the footway load on the lane defined for the footways. As we said, the software itself will change the position of lane 1, lane 2 and lane 3, switching between them in order to define the worst solution for the element that you are going to assess. Another tool very useful for the definition of loads is for the temperature gradient to the bridge deck. In fact, you can find some typical cross-section diagram for the gradient temperature according to different norms. So you can apply in a cross-section not only a gradient, linear gradient on all the section, but even different gradients as defined in the different norms. You can define very easily the spectrum for the analysis according to the local norms that you're going to use, defining the peak ground acceleration, soil conditions, and all the parameters that you have to define. And you can obtain it very easily. Even you can do some analysis for time history using recorded accelerograms that are in the library. Design and checking can be done according to the main norms for reinforced concrete, for steel structures, for composite, for pre-stressed concrete. And there is also a general section designer for any kind of sections, material, reinforcement, etc. This is an example for designing checking of steel elements using Eurocode 3. You can define safety factors according to national annex. You can select safety, serviceability limit state parameters, and the output is very clear with all the dimension of the cross-section, the combination load that are going to be analyzed, and all the values and analysis with the results of the check. The same for the concrete, selecting in this case a Eurocode 2 and changing the factors according to the national annexes. Even here the output is very clear with all the information that you need to check. And also very important, the possibility to design and check composite cross-section using Eurocode 4, defining slab reinforcement and inputting the effective width of the slab. The software can evaluate the class of the section, class 1, 2, 3, 4, and define, in case of class 4, the effective geometry of the cross-section. And for the assessment of the composite cross-section, it is also possible to have the design of the shear connector, define numbers and characteristics, tensile strength or diameters, so you can obtain the final assessment of these elements. The design of the composite section is executed according to the formulas in the Eurocode 4 and the Eurocode 3, and it is very common the case in which the web is in class 4. So the software can evaluate the slenderness of the web, considering also the stiffener that we've used, and it can define the class of the cross-section and define the effective area and the effective geometric characteristics using these formulas. And the first bridge that we are going to see is the high-speed rail viaduct from Bangkok to Utapao in Thailand. This is a very long viaduct, 168 kilometers from the north of Bangkok to the south part of Thailand. The viaduct will connect 3 airports, 2 existing airports in Bangkok and 1 airport in Utapao. The viaduct is composed by several simply supported spans, 30 and 40 meters long. The cross-section with a double track is a box girder, precast and post-tensioned. The model in this case is very easy, and it is generally done by a single beam in the neutral axis of the cross-section. In this case, the cross-section is the same for most part of the beam, except for the edges where we need to increase the thickness of the lower slab of the box girder. Post-tension has been applied through pre-stress loads. In this model, only the actual altimetry has been inputted, but it is possible to define also the actual planimetry if requested. In the definition of the pre-stress strength, the geometrical characteristics and the loss of pre-stress effects, relaxation, friction, wage loss, and the applied load at the end of the strands has been inputted. One of the main issues in the rail bridges is the interaction between rail and the structure. Having the wrong welded rail connected to the deck by the ballast, the deflection in the deck due to the thermal effects, training load and braking force will cause stress in the rails that have to be assessed. Unfortunately, the behavior of the ballast is different in case it is loaded or unloaded. So the analysis needs to consider this different situation. This analysis can be performed using the construction stage analysis, in which, as the position of the train changes, the behavior of the ballast changes accordingly. In the Midas Civil, there is a wizard to create a model with rails connected to the deck, with a link with appropriate behavior, and the construction stages modeling the train running on the rail and the link changing their behavior accordingly. In Midas Civil, also masonry bridge can be modeled. In this case, 3 bridges on SP38 in Italy, in Sicily, the south part of Italy. The design was for the rehabilitation of the 3 viaducts due to the fact that some local collapses happened during 2015. The bridges have been realized during the 50s of the last century using local stone. To rehabilitate this bridge, an intervention is being proposed, inserting micropiles inside the masonry piers, and to take into account the fact that some of the piers can be collapsed in the future due to the weakness of the local stone. The model considered also the situation in which all the superstructure was acting only on the micropiles. Arches and walls have been modeled using shell elements with masonry properties, and some special shell elements have been used to connect arches with pavement. In this case, for the moving load, an influence surveys has been used to better have the evaluation of stresses in the arch. With the influence surface, you can obtain the worst position of the moving load in both directions, transversal and longitudinal. Obviously, you can find the forces in the shell elements represented here with colors and the legend of the values, and the deflection for seismic actions. Composite bridges are very easily modeled in Midas Civil using the wizards and all the possibility that you have to define the elements. Bridge over Buna River is a new bridge in the area between Albania and Montenegro, across the river Buna that represents the border. Is a 320 meter long 3-span composite bridge with the central span of 145 meter long. The approach viaducts on both sides of the shore is potential in concrete. Here, the longitudinal profile of the new viaduct over Buna Bridge, with the 2 approach viaducts in concrete and the composite part of the viaduct in the middle. 145 meter span across the river and a 2-side span for a total length of 320 meters. And these are the cross-section of this bridge. In the mid-span we have 2 box girder, composite steel concrete, with 1 carriageway and 2 lane for walkways and a cycleway. And this is near the pier, in which we have 2 different elements. The first one is similar to the mid-span, and the second one completely made by steel. And this is the list of the norm that we used in this bridge. The bridge is completely based on the use of Eurocode. So Eurocode 0 for basis of structural design, Eurocode 1 for actions on structures, and 1 part 4 for wind actions and 1 part 5 for thermal actions. Eurocode 2 for the design of concrete structures, 3 for the design of steel structures, and Eurocode 4 for the design of composite steel and concrete structures. And finally, Eurocode 8 for the design of structures for earthquake resistance. In this case, obviously, we've used also national documentation for meteorological situation to define the wind speed and also to define the peak ground acceleration. In the finite element model, it's easy to understand the different section type basing the difference by the color. So you can actually understand if you have defined correctly the difference between segments and others. In this case, the piers are inside the river, so the shape of the piers has been considered to not to create trouble to the flow of the water. Foundations have been considered on piles. In this case, the cross-section is composed by two box girder beams with a slab on the top made by concrete, and this cross-section is easily defined using the library in the software. For example, here you can define the width of the concrete slab and the thickness of the concrete, and all the dimension of the cross section made by steel. You can define the stiffeners if they're flat or they are U-ribs or something else, and you can define the ratio between the Young modulus of the two materials and even the ratio in the different phases considering creep and shrinkage. In the show calculation results, you can read all the characteristics of the geometry in the first phase with only steel acting, and the second phase with the concrete slab acting. In this case, we've used the pot bearing, and the pot bearing are modulated with an elastic link in which the different direction of movement can be activated or deactivated. It is possible also to use different kind of bearing devices using the library that is present in the software, and in which you can find also rubber bearing, elastomeric bearing, or isolators, or friction pendulum, or other kind of bearings that can be used in your model. Here the construction stage for this bridge. Macro phases of construction stages are these four. In the first one, only the segment over the top of the pier has been erected, and then going ahead symmetrically on both piers with the other segment, and finally to close the deck and to cast the slab on the top of the steel deck, and in the last phase, of course, pavement and permanent loads. It is important in this case the possibility to change the boundary condition from one construction stage to another. We need to have a restraints in this point during this construction stage, and we have to release these constraints at the end of the construction. And this is possible in Midas, changing the boundary condition in every construction stage. And here the results for the different stages of the composite bridge. So the first stage you have only piers. The stage 2 you have the two main segments on the top of the pier, and in this situation there is a restraints from the pier and the deck in order to ensure the stability. And going ahead in the stage 3, we can see that we cast the slab on the top of the steel deck, and in the stage 4 going ahead up to the final configuration. And after the overview of the most typical bridges and cross-section that can be used in a Midas civil, we want to analyze with more details two particular bridges. The first one is a tied arch bridge in Albania, a bridge across the Drin River in the internal part of Albanian Firs. This is the Drin River immediately after the dam of Firs, and the existing bridge, this is one that you can see in the lower part of the picture, can't be used anymore for the fact that the clearance is less than necessary. So the proposed is to realize a new bridge, that is this one on the upper part of the picture, and this new bridge doesn't have any support inside the river. The tied arch is simply supported on the abutments on sides of the river, and the total length of the bridge is 120 meters. The cross-section is composed by a single arch in the middle of the bridge, made by steel with a trapezoidal shape, and a composite section for the deck with 2 carriageways and 2 walkways. Foundation has been proposed with micropiles due to the fact that the subsoil is made by rock and it was impossible to realize great diameter piles. Construction stages are very important in these kind of bridges, and considering the fact that we have the dam near to here and the quantity of water can be arranged as we need, we propose this kind of solution, decreasing the width of the river during this phase and realizing temporary piers on both sides of the river. So the deck can be erected in 3 stages, first starting from the abutment up to the center and erecting the center part of the deck. After that can be erected also the arch on both sides using the same alignment for the temporary piers and the central part of the arch. Once the arch is closed, temporary piers between deck and arch can be dismantled and hangers can be erected. And after that we can dismantle also the temporary piers below the deck, and we can go back to the original situation for the river. The same construction stages has been modeled in Midas civil. So you can see here 4 main stages. The first one with the 2 segment with only steel acting. In the second one, this is represented the other part of the segment with the concrete slab acting, and the central part with only steel cross-section. In the stage 3, all the slab has been activated and the arch start to be realized. And in the stage 4, all the deck, all the bridge has been completely realized and the temporary support removed. For composite section, it is very important to define the different stages between only steel acting and the composite section acting. It is possible to do that defining the different stages in which the different part of the section will be active or not. So in this case you have the first stage in which only concrete, so-called part 1, can be react on the loads, and in the second stage the completely cross-section will be active. And this concept is clear in this slide, in which you can see here the stage in which only the steel beam has been activated and so self-weight wet concrete 4 more loads are applied, and their effect is evaluated only for steel action. In the further stage, the concrete slab is activated, and you can see in the model like that, and all the loads applied since this point will be effective on the composite section. The way in which you define the construction stages is to define groups for elements, groups for loads, and the groups for boundaries, and to activate or deactivate these groups inside each stage. So once you have defined the construction stages and the length in days of each construction stages, inside them you can define which group is active or not active. There's also a table to check the activation of groups and in order to be sure of the model that you have done. For each stage you can have all the results that you like. So deflection, for example in this picture, you have the deflection of the outer part of the deck, the inner part, and the final configuration. And deflection is also very useful for the camber that have to be designed for the project. And of course also bending moment in every stage. This is in the final stage, actual force in the final stage, but you can check obviously stresses in the elements and reaction and all the characteristics that you need to check. And as said before, using construction stages it is possible to generate the general construction camber and manufacture camber, having the results on graphs or on table, so you can use this table to put these values in the drawings for the manufacturer. The last bridge that we are presenting here is a cable-stayed bridge designed for a new road in Logara, a location of south of Albania. The new tunnel is under construction now, and at the end of the tunnel this bridge has been proposed. The cable-stayed bridge has the main span 110 meters long, and it is on curve with 2 planes of cable strays, and for each plane there are 7 cable stays anchored on the back of the bridge directly to the soil by an anchor block with micropiles for foundation. The pylon is founded directly to the rock, and it's 25 meters tall. The cross section is a composite section with high-shaped beams at the edges and I-shaped cross beam and concrete on the top. One of the main issues in this kind of bridges is to define the initial stress to assign for each cable stay. For example, in this table there are the loads, the stress for each cable for this project, and this is important because you have to know what is the stress in each construction stage in order to have in the final configuration the stress that you want to have and the real geometrical configuration that you want to obtain. There are different ways to analyze the model in order to find the initial stress in the cable stage. Mainly we have a backward analysis and forward analysis. In the backward analysis, in the final configuration, the cable initial stress force for self-weight and additional load is determined. Starting from the final configuration, we can start to dismantle in the deck, obtaining the initial stress for every stay cable and the time of installation. In the forward analysis, stage construction are modeled simulating the actual installation of the cable stays. So the first stage in the backward analysis is the final configuration. The first stage in the forward analysis is the actual first stage. In the backward analysis, initial configuration may be obtained through unknown load factor in the Midas civil, but non-symmetric configuration or time-dependent effect cannot be considered. Forward analysis can be generally performed after backward analysis to evaluate time-dependent effect. In Midas civil, forward analysis can be performed without backward analysis, and this is one of the main points that Midas civil add to this kind of model. In the backward analysis in Midas civil, you can use unknown load factor function. The unknown load factor function can be explained in this flow chart, in which the step 1 is to define the model of the final configuration of the cable state bridge. Once you have to do that, you have to generate load conditions for dead loads for main girders and the unit pretension loads for cables. So, in other words, all the loads that are on the bridge, but just unit load for each cable. In the step 3, input dead loads and the unit loads, and in the step 4, the load combination of dead and the unit loads. At this point, you can calculate the unknown load factors that will be the factors to apply to the unit load to the cable in order to have the desired configuration. You can do that using the unknown load factor function. The table of the unknown load factor function is represented here, and you have on this row, for example, the restraints that you have considered for some nodes, and on the top the factor that you have to apply to each cable stay to obtain these results. So finally, you can review the analysis results and calculate initial pre-stress as requested. As we said, in the Midas civil, forward analysis can be performed without doing the backward analysis before. This is possible through lack of fit force analysis, in which additional potential load during cables installation are calculated. How do that the program? The displacement at each end of the cables are calculated at the stage immediately before the cable are installed. So, using the displacements at each cable end, the program calculates the additional cable pretension and the difference between the cable length at the completed state and the cable length during the construction. This additional cable pretension is added to the initial pretension, determined from the initial configuration analysis. So this value is entered as the pretension during the construction to perform forward analysis. So in this case, you can consider time-dependent effects and also non-symmetric configuration. Lack of force fit analysis can be added to the model, just considering this control in the window of the analysis option. The flowchart is defined here, and the analysis starts with the final stage analysis. After that, assigning constraints satisfying initial equilibrium state and you can perform construction stage analysis. After that, you have to verify the member forces. If needed, you go back adjusting cable protection. Otherwise, you go ahead specifying design cable tension. Then you can generate camber for a tower and a piece girder, and you can go to the construction stage analysis considering camber. You have to compare final cable tension and design cable tension, verify cable tension at each stage, and verify member forces at each stage. In every step, you can be obliged to go back and adjust the cable pretension, starting the construction stage analysis considering camber again. Once you are here, you have to compare the final displacement and the camber. And you probably need to adjust the camber for the tower and the PC girder and to go back to this point. When everything is good, you can verify the member forces, and finally you finished if it is okay. Otherwise, you have to go back to adjust design cable tension and to go to the construction stage analysis and repeat all the flow chart up to the end. And now we can analyze the construction stages for the cable stayed bridge in Locarà. So in the first stages, foundations, pylon, anchor block has been erected. The first segment of deck has been erected, fixing it to the pylon. And the second segment, anchored with the cable stayed to the top of the pylon and to the back side of the bridge, have been erected. Initial stress in this cable, evaluated with the forward analysis, have been applied. The sequence of construction stage is very easy. Other segments will be installed, and for each segment 4 cables stay, 2 on the front part of the bridge and 2 on the back side, will be erected and stressed as defined in the procedure of lack of fit analysis, arriving in that way at the end of the bridge when the last segment is installed. And this is the model realized for that bridge in the final configuration, in which the cable stress and the ultimate limit state load combination are considered in this picture. To arrive to this final configuration, the construction stage analysis has been performed, and you can see here some of the construction stages. This is the first one that we have seen in the picture before, with 2 segments installed and 4 cables stayed, and the first segment with the slab active and the last segment with only steel active. Proceeding up to the end with more cable stays, and this is the final configuration before the last segment to be erected. Time-dependent effects have been considered in this model for the concrete slab. So creep and the shrinkage effect have been defined, and considering CHEB FIP 2010, values of characteristic strength of concrete, relative humidity, notional size of member, type of cement, age of concrete at the beginning of shrinkage, and type of aggregate has been inputted here, and the curve for shrinkage strain and for creep coefficient have been obtained and applied to the concrete during the construction stage analysis. And finally, I don't want to bore you with the results. Of course, you can obtain all the results that you like. And the only thing that I want to show you is the possibility to display the current displacement and the stage real displacement, that obviously are different. And this is very important for the design, for the camber, but also for the check during the construction. So thanks for your attention. I want just to greet you with this amazing picture, very thrilling for me, taken some months ago from the top of Braila suspended bridge across the river Danube, a project in which I've been involved when it was in the feasibility study phase. Here my contact, the website, the mail address, and that's all. Have a nice day.